Hi everyone, we are Team Car-Tooning and the problem we are addressing is traffic. Traffic is a problem in every major city in the world. Loss in productivity costs the US economy more than $87 billion a year. This excludes the costs of vehicle repairs from the fivefold increase in accidents, vehicle maintenance costs, and the healthcare costs associated with pollution. Reducing the number of cars on the road has proven to be difficult. Even with the rise of autonomous vehicles, McKinsey predicts at least a 2% increase in car sales every year. Public strategies attempting to curb traffic include HOV lanes and congestion pricing. The former has actually been shown to increase traffic due to the underutilization of the road surface, while the latter has also been proven ineffective. Fortunately, the advent of autonomous vehicles provides a new method for reducing traffic: platooning.
Platooning is a method for autonomous vehicles to coordinate their velocities to reduce or eliminate traffic. This is enabled by a variety of state-of-the-art technologies, each with their own standards. AVs require superhuman driving performance with lower reaction times as the fastest human, as well as deterministic and reproducible fail-safe control with performance margins in case of emergencies. Furthermore, 4G communication is constrained by maximal communication data rates. These standards lead to a tight set of specifications. Efficiency-wise, we constrain ourselves by the 3G minimum data rate of moving vehicles to have performance margins relative to the 4G communication data rates. We must also satisfy the system's safety-critical standard of producing outputs within 20 milliseconds of gathering the data. The controller must be reliable and deterministic, and we must be able to model it. Furthermore, to solve traffic, our solution needs to be scalable to arbitrarily sized platoons. We also need a certificate of stability to prove the safety of the system. And finally, our solution must be capable of adapting to evolving tech and standards.
When designing a novel networked controller, several different design paradigms need to be considered, each with their own trade-offs. Continuous time controllers can better model system dynamics. However, they are difficult to incorporate into constrained optimization frameworks. As we plan to use such a framework to handle the constraints from the previous slide, we choose to design a discrete time controller. A centralized control scheme scales poorly to larger platoons, incurring additional network delays and decision times as the platoon grows. By contrast, a distributed scheme can scale to arbitrarily sized platoons without these two effects. Finally, control strategies fall into two general categories. The classical theory of PID control focuses on tuning gains to achieve a specified performance. However, this theory leads to provably unstable controllers for platoons larger than two vehicles. The modern approach to control synthesis uses an optimization-based framework to obtain control decisions, putting the design burden on the cost and constraint functions to achieve the desired behavior. Car-Tooning leverages this modern machinery. The Car-Tooning controller is designed as three asynchronous optimization problems. The first tier of the hierarchy, two semi-definite programs are solved using information about the current communication delays present in the system. The output of these programs are two matrices corresponding to the effects that this time delay has on the system dynamics and the responsiveness of our actuation. In the second tier of the hierarchy, a standard model predictive control problem is solved, where the objective is to minimize the cost of our anticipated trajectory and actuation. The first constraint requires that our vehicle obey the current system dynamics, augmented by the delay effects computed in the previous tier. The second constraint is Car-Tooning's stability certificate. By maintaining the magnitude of the velocity transfer function of the current vehicle and the downstream vehicle's velocity below 1, Car-Tooning ensures that changes and errors in the current vehicle is not amplified downstream. Achieving this constraint certifies that our controller is preventing traffic buildup. The third constraint quantifies the level of stability at the current node. Gamma near -1 is more desirable, as it implies more stable platooning. But this comes at the cost of large increases in inter-vehicle distance, and so its minimization must be balanced by other performance metrics. We will unpack the specifics of the programs in our demo video to follow.
The Car-Tooning controller satisfies all of the aforementioned specifications. It achieves efficiency, as the bottleneck to the number of cars one can communicate with is the current range of vehicles' communication systems and not 3G data rates. It satisfies the speed requirement, as processes solving the quadratic and semi-definite programs can be easily scheduled on an i5 chip to output decisions within the given deadlines. It reliably produces unique solutions to all problems via convex optimization. It can scale to arbitrarily sized platoons thanks to its decentralized nature. It is provably stable and robust, even in safety critical situations, thanks to the first to our knowledge stability certificate. Finally, it is flexible to the adoption of new standards due to its abstract formulation. So in order to validate our theoretic developments, we work to integrate Car-Tooning into as realistic of an autonomy stack as possible. This is a block diagram of our autonomy stack, where in green, we have data visualization, in yellow, the autonomous lane keeping and the central processor, and in blue, the Car-Tooning velocity motion planner. The data visualization retrieves the steering and velocity data and plots it in real time. The steering controller uses vision-based track detection to autonomously maintain the car on the lane. The Car-Tooning controller solves the programs identified previously and outputs the desired velocity command to the central processor. As you can see, Car-Tooning integrates naturally in the place of any velocity motion planner. It can either serve as the primary planner or in an advisory role to more complex velocity planners.
We consider the potential ethical dilemmas related to autonomous vehicles. Autonomous vehicles are expensive and risk creating two classes of citizens on the road: those with autonomous vehicles capable of high throughput and those restricted to slower lanes of traffic. A poorly implemented platooning algorithm could actually make traffic worse through large inter-vehicle distances or unstable oscillations. Finally, driverless vehicles may contribute to unemployment, as 3% of Americans operate a vehicle as a living, and truck driving is one of the most common jobs in 29 states. Due to the emergent nature of the autonomous vehicle industry, the relative influence of each stakeholder is difficult to predict and will likely vary across the globe. Car-Tooning's flexible business model aligns our incentive structure to the dominant stakeholder in various markets, ensuring the project's viability no matter the evolution of the industry. We demonstrate 3 likely scenarios in various international markets. We will discuss the business model in more depth in our demo video to follow.
That's it.
All right, thanks team. Can you send the link to